Hello, everyone. I'm Anmol and Satyajeet, and we're both master students right now at the Music Technology Group in UP of Barcelona. Uh, so this work was inspired by basically I'm a DJ and Satya is a music producer, and this work was inspired by a shared love for making beats, and we were specifically inspired by this swing or groove in the Latin American rhythms. And that's what we are going to talk about today. In fact, the preliminary nature of this work was also presented at Izmir this year. And we have some more experiments now. And yep, let's maybe proceed with the talk. So, yeah, just stating like the inspiration again, we wanted to bridge the gap between the algorithmic rhythm creation, which is, let's say, a lot more quantized and grid like and sounds very machine like, and maybe bridge this gap between the expressive qualities of a live performance, where the mistakes, let's say, are not so much mistakes, but a part of the performance. And how we do it practically is like we build an algorithm, which we're going to talk about in the talk. And then we are very, being musicians ourselves, we really wanted to make our research usable. So we wrapped our model, the neural network model, in a VST plugin so that people can use it, and we're going to share the GitHub repository where it's there and you can download it and basically start using it. So I want to talk maybe a little bit about the overview of the presentation. So we have, first of all, we're going to talk about the, if you see on the top left, the Candombe drumming style, which is the one specific style that we want to show to you. And like because our technique works for style specific rhythms, because every style has a unique groove. And the method is general, but we can extend it to any methods. And that's what we're going to talk about. Then on the right side, you see more technical or more engineering like stuff on how we actually mathematically represent some of these ideas. And finally, in the center is the VST plugin that we make and that we want to present. So for maybe, let's say, the non-musician audience in the audience, we want to talk a little bit about what microtiming and grooves are. And I'll have Satya present that part.
So yeah, this work is based on this core concept of microtiming, right? A lot of you may or may not know the exact technical understanding of this, but I promise you that you've heard it and you know what groove is and you know what feel is, in rhythmic expression. So technically though, microtiming is subtle deviations from a strict metronome-like or grid-like timing. So if you look at any of the images on the left, you'll see that there's a grid, right? And it's an equal space grid. But humans don't perform like robots. So these subtle deviations are called microtiming, where the notes or the beats, they come slightly ahead or slightly behind the expected positions on the grid. And this is what we understand as feel or groove. And we know this, we have heard it in all kinds of music, like in Western, you have jazz and even hip hop, like lo-fi hip hop. We love it. So, and especially in India, we have so many folk traditions, street music, we are very familiar with it. And so that is microtiming. But now there's an extension of this term, which is a generalized term called microrhythm. And it basically says that groove is also represented not just by timing, but also by other aspects like dynamics, and then timbre can be one of them, like duration or central frequency. Now, I'll just give you a small audio demo of how this concept of microtiming affects groove, okay? So this is something which is quantized. Quantized means everything is locked to the grid. So this loop, every drum shot sound is at the same volume and locked to the grid, right? Very robotic. Now we add one layer of humanization to this. So the drum hits are coming in at different loudness or dynamics. So So that accent is already giving you that feel, right? Now let's add microtiming to this. So just using dynamics and microtiming, we are creating so much expression, right? So that's the basis for this work. And now coming to Candombe drumming. Candombe drumming is very specific style of drumming, a street style drumming from Uruguay in South America. And this is the focus of our work. I'll just play a small clip of what it sounds like. So like you see, there are 3 drums. It's a 4/4 pattern, but the way they groove, the way they swing the beats gives that unique expression. So it's not random. They are in sync with each other, and they are moving the notes away from the grid in a very conscious way, right? So there are 3 drums. One is called Chico, and piano, and repique. Which each of them has their own microtiming pattern, and this will be relevant later in the work. Okay, Anmol will take you through the engineering part of this now.
Yep. So after having talked about the musical meaning of what we do, let's go a little bit into the mathematical representations that we use to model this phenomena. First of all, you can think of a quantized grid as simply a 2D matrix where, let's say, your y-axis, if you look at the figure down below, let's say if you're aware of the concepts of beats and bars. So one bar has like 4 beats, but one beat also can have 4 subdivisions. And these are these 16th note subdivisions that are like the most common representation used in popular music. And what we do is that if we model sequences over, let's say, 2 bars, which are, let's say, in our case, we find that those are the lengths over which patterns repeat. So you can model these 2 bar sequences, which would then be 16th note subdivisions for 2 bars. So that's 32 total time steps quantized. That's your x-axis. And the y-axis is, let's say, different instruments. So for our case, which is Candombe, there are 3 different instruments. So these 3 different channels, let's say. And modeling each of these channels is important. Now, the first matrix would be the hits matrix, where it's this 32 cross 3 representation, but it's a binary matrix, where at each time step, you know where there's a drum hit or not. Then there's 2 other matrices, the velocities and offsets, which are of the same size. And the velocities offsets actually has this information about the MIDI velocities or the dynamics. And we simply scale, let's say, the values from 0 to 127, the ones who are aware of MIDI format, between 0 to 1. And the offsets are actually this microtiming information, because the hits pattern is just binary, and that's what leads to the quantized formulation. Now, how we go back to adding this timing information is through the offsets. And these offsets are from minus 0.5 to 0.5 at each of the hit positions where there's a 1 hit. And it goes minus 0.5 to 0.5 because it's like you can either have this beat shifted, let's say, negatively in which is like a bit quicker to arrive, or it can be slightly delayed. So it will be like a plus positive 0.5 shift. So once you have this mathematically modeled out, we have some more information here about our specific data set on how we extract these informations, but this is the key idea here. And now it's the model architecture part, where we actually, it's a transformer based model, and we go from, so before going into the depths of the model, we go from a very, let's say, just the hits matrix, which you see on the bottom left, to the offsets and velocities matrix, which as explained in the previous slide, is the part which actually adds this performance information. And in the general terms, we call this going from score to performance. And how we do it in a transformer is, so we have like an encoder only transformer, where we project and there's some interesting technical details here which we had to. So if you're aware of, let's say, how language models work, you have to tokenize things and stuff. But somehow we find out we actually do not need to, because these representations by themselves are already, let's say, some sort of word vectors. These are interesting details which maybe if some of you are curious, we can talk about later. These were in fact the key details that were very popular at Izmir this year, like because they concentrate a lot on the computer science of it, but it's not very musically relevant, so I'm kind of not going to go so much there. So for let's say a few more details about the model, it's a multi-head self-attention with 4 heads and model dimensions. And again, for the losses, it's a simple mean squared error. So once we have these performances, like once you learn, let's say, this model from a dataset, you give it a hits matrix and you get the offsets and velocities. Now this is interesting because once you learn this groove from a style, not only can you, let's say, get the style back for the same hits, you can actually take these hits, the score patterns from other styles, and see what groove the model adds. So you can maybe, let's say, take some style and play it in the style of another like genre. And so this groove transfer thing is also something that's a direct application of the way we model these rhythms. So here we have some experiments, and I'll probably invite Satya again to talk a bit more about it.
So yes, how much time do we have?
We have it.
Okay. So experiments. So now that the data is represented, we had about 35 minutes of data then which got represented in the way Anmol explained, HVO, hits, velocities and offsets. You train the transformer, and then how do you know whether it has learned something? So you need to do some experiments to evaluate, and for that we use the musicological understanding of Candombe. So and in Candombe, like I said, there are 3 drums. One of them is called a chico, right? And the chico is a timekeeper drum, and it plays the same pattern over and over in every beat, right? So what we did is we took our input data, and then we took the predictions from the model on the chico hits, and we plotted the distribution, and we see that from the distribution, it's very small. I know you can't see all the details, but just to give a general idea of the experiments, that you can see that the distributions are similar. They're not identical, but they're similar. So it means it's learned a general sort of representation. Same with the velocities of the chico hits. So it's learning patterns within a beat, and in the same way we did experiments with patterns at the level of a cycle. So there are patterns called clave. If you're familiar with Latin music, there are patterns which play repeatedly over a bar. They're called clave patterns. So we did the same experiment. So again, it learns the distributions over a cycle. So I will not play the audio examples now. We'll keep the time for the final demo. And so this is the interface. So this plugin, you give it your quantized MIDI file, and you press the humanize button. It adds the groove and velocity, the timing and the velocity, and you can drag that out, or you can play it with the stock samples inside the plugin. Yeah, I think we can play the demo now.
So if you heard throughout the performance, like you could definitely felt how when we go from the quantized pattern to humanized, there's certain groove to it. If you're a musician, it would be much more obvious. And there's one more thing, let's say for the engineers in the audience, if you look below, you can see these distributions of velocities over the entire performance. And if you're aware of the Ableton interface, and if you look at the, let's say the quantized sections, these are all like the same velocities, right? And these are all the same velocities here in the bottom. And these, let's say, are the technical variations which actually add this performance element. Also the timings, but there are too many notes here, so it's hard to see these variations, let's say. And yep, so I want to talk about like why we are here at the ADCx India, because there are a lot of Indian rhythms that have very similar properties, and that's something that we want to explore. And I just want to play, let's say, a tabla sample, and it's very, very evident how groovy it is. So using something like what we do, you can have these same groovy tabla feeling patterns added to some other drum sounds. So let's say you play Latin drum sounds on and you feel tabla like grooves over there, and that's the kind of stuff that we're very interested in. At the end, I'll just want to talk about some of the, let's say, challenges of our work. So there's a huge dependence on data here, which is one of the reasons why we worked with the Candombe dataset, because it was publicly available for such a use case. Now also and for Indian datasets, it's a bit hard to find, and we've had a chat about this today morning with some people here as well. The ethical implications, that's also important, because we don't want this to be something because there are a lot of cool grooves found in very folk traditions. We don't want this to be a tool that replaces those artists' livelihoods. It's more about, and that's why we claim also, which is also very true, that it's never going to be as good as a human performer. The idea is that someone else can sample the rhythms from some different style, and if you then, some other person from some other part of the world, and then if they really like some particular style, then we hope that this will lead them to actually work with the musicians from different parts of the world. And so the opportunities it provides for us and to the ability to study various rhythmic cultures within the same framework, and what we want to again provide in our tool base. So we want to add more styles, so that music producers can have richer algorithmic rhythm creation tools in music production. So thank you so much, everyone. And you can scan this QR code to check out our VST plugin. And that's all from us. And thank you.
Hi, thank you so much for that presentation. I would like to learn more about the Candombe dataset itself, and also the categories and how it's structured. And secondly, what do you like the dependence on data? What do you estimate as like the minimum threshold and like a decent threshold for good performance of the VST?
So the first question about the dataset, I think I understood that. So I'm going to first answer that. It's structured as what we have is for each of these, let's say 3 different drums, we had 3 different mics. So we had already 3 different channels. And to talk about, let's say it's because it's already labeled by human annotators, so it's very accurate for our tasks. So the actual drum hits at the times were labeled, and also the beats were also labeled. So you have like a beat grid already, and the actual drum hits for each of these channels. So then from that information, it's very straightforward to get to this deviation mapping. For the velocities, what we use is some MIR tools for getting if you're aware of the concept of onset strength, and use that as a proxy for the velocity. So these are, let's say, the technical details of the dataset. The second question, could you repeat that? No, I think I didn't get it exactly.
It's more about the size of the data required for the performance to be good.
I see your point. So the thing is that for this, let's say the general task, we had there's a very large data set for not genre specific grooves, but other grooves like MIDI samples. And then let's say if you already have MIDI performances directly, then it's super easy to go from those to quantized performances. And we use that for, let's say, the pre-training part of it. So we already are in some solution space. And then this part of the work is done with actual audio recordings, which is why we need to do these extraction stuff. But then you don't need way too much data if you're like fine tuning, let's say. I mean, the exact, so we can maybe discuss later on what the numbers would be, but for our performance stuff, it worked fine enough. In fact, like if you're doing, because we do a generative model, it's not exactly correct, but like you kind of want some sort of overfitting. You kind of want to be able to sample from a style specific.
Absolutely, yeah.
Yeah. So I guess, yeah.
Cool. Thank you so much.
Hey, thank you for the presentation. Do you see the methodology or the approach itself also to help with what's called assessment and learning as well? So since you're modeling deviations, well, what's called deviations from a standard grade, both in terms of timing, dynamics, and other dimensions here.
I think I didn't.
No. Do you see an opportunity also in helping? Of course, this is music creation, but also the music learning of it. So if I want to learn, say, Candombe, and then learn it like a human, would this kind of a methodology be useful as well?
So when you say learning, you mean learning by a model, right?
Learning by a human.
By a human, okay, as an education.
As an education tool.
Yes. Let's say. Oh, I see. So you mean once the model is ready, then like they can use it to listen back, or like how these deviations are. And sure, yeah. Let's say, for sure, yeah. Please.
So like if you're a student of Candombe, right, and you perform and you record it and you use it to evaluate whether this student is performing the right groove or not. I understand the use case, very interesting, but at this point this is very challenging because like we said, to get from audio to that format which is learned by the transformer is a slightly challenging pipeline itself to go from. So that's why we specifically worked with this Candombe dataset, because they have created this rich dataset which goes from audio recordings to human annotations. So that's why data is always a challenge in this kind of project. But I can completely understand like how this could be a useful application. But once that pipeline is ready, which can go from audio recordings to a very nice sort of allocation of every onset to a subdivision, if you have that, some way to do that, then opportunities are like many. Yeah.
Right. Yeah. Thanks.
Hey, the dataset that you mentioned, right? Is it tailored based on the choice of artist that you've picked?
Yes. So this is I think that's a good thing. That's what we want. In fact, like this makes it in fact customizable for each artist. Let's say you are a band and you want to learn your groove, then you have a set of your own recordings, and then you throw it in this model and you get a model specific to your groove. And that's very important for musicians, to be able to have, let's say, tools specific to their style. So when we say it's like a Candombe like data set, of course there's implicit assumption that it's for these specific artists, the way they've performed it. However, what we do observe even in musicological studies is that these random deviations are not completely random, and there's a pattern to it. So you can find these similar deviations in other performers as well. And when humans perform it, we would expect our model to be able to learn this general representation of the style. But if, let's say, a particular musician has some of their own variations on top of it, they get learned as well. Yeah.
Nice. Thanks.
Hi, thank you for your presentation. So I just had one question. I'm sure you would have tried sort of collecting audio and then creating a data set without human annotators, because I would think with a drum like this, it's just one sound, like unlike a tabla where they play on different parts of the tabla, this is just one sound. So did you try using like maybe an onset detection to cut it into strokes, and then you would get the timestamp which you can translate into like a tick value or something? Did you try something like that? And did you face any challenges?
So, I mean, yeah, that's a very good question.
Tell them about our assignment itself.
I think first of all that would be like very difficult, especially in the case you say where there are multiple sounds. I mean, that's almost like any of so, and I think like we have at least a way, or like how we think there's an easy way to avoid it. Where if you, because even in this case, the Candombe dataset has been specifically recorded. So these days there are these, let's say, these surfaces for electronic surfaces for something like tabla, and there are these, and there are performers who actually perform tabla grooves on these electronic surfaces, and from then on you entirely skip this problem of having to actually like label these, let's say, annotations. And if you have a bunch of players playing on these electronic tabla heads, you get this very detailed annotations automatically, and as soon as you have it, then the rest of the pipeline follows well. So when we were actually discussing about we would do it for Indian rhythms, that would be the case. But these surfaces are kind of expensive for grad students, so it's we're looking at ways on how we can build forward with this.
Also, like,
You go on the mic.
to answer both of your questions, like this started as an assignment actually in our course. So we thought we want something to learn to help us do J Dilla grooves on drums, if you're aware of hip hop, J Dilla. And we started with that. We took some audio recordings, tried to go from that audio to that, and it fails at many different stages, if you want to go. And that sort of stops you from even approaching this problem. So we said, okay, for now, we'll skip that pipeline. We'll work with ready-made data in this format. But yes, you're right that technically that's what we are supposed to do. Like if you find a recording of any particular style, you should be able to go from there to this. But there's a pipeline that needs to be really, developed, which goes from that to that hits velocity offset format. That's a little challenge at the moment, yeah. But
Okay. Thank you so much.
Yeah.
Any other questions?
Possibly trivial question. This Candombe dataset that you're talking about, how big is it? Like,
we read that. I think it's like around 40 minutes of recordings.
Oh,
Yeah, it's that's.
So there's a project called Interpersonal Entrainment in Musical Performances. So they have 3 or 4 different rhythms, including North Indian tabla, I think. But it wasn't as rich as Candombe. There's also Malian Djembe. So you can look it up. Interpersonal Entrainment in Music Performance, IEMP dataset. Yes.
Oh, hi. Thanks for your presentation. This is something that I relate to because I do a lot of drums programming for my own music. I used to, at least. One thing that's challenging is I know where a certain hit has to be placed, but how a drummer would really play would be completely different. It's not just the timing, but it's also like adding ghost notes, right? Would something like this be extended to mimic a human performance? Like, let's say I just know rock music 4x4. I know kick, snare, but fill the rest of the space.
Yeah, no, that's in the current format, nope. Because let's say if you don't have the hits mapped out, then however, I think where we are, let's say, differing is how you're thinking about this score, this kicks. Like, let's say if there's a ghost note, we would still at the ghost notes have like a 1 in our hits matrix, even though with a very low velocity. So if you're purely doing our framework, you should be able to get that. But strictly speaking, then that would not be in musicological sense the purest score. But our model actually doesn't have that problem. It's just a very low velocity hit. That's how we treat it as. That's how we treat it as.
Okay, yeah, thank you.
Yeah, thank you. We can move on to the next talk. Yeah, a round of applause for both of them.